As he was saying, you take the shit. Yeah.
Take the derivative, you set that derivative equal to 0, and that will give you the minimum. It also gives you, incidentally, the maximum, but in this case we're talking about the minimum. So if you take the derivative of the tangent vector and set it to 0, you will get, as it were, the path for the geodesic, the shortest distance.
No, there was no way
now,
that brother,
when I say
given the
take
gas
the derivative,
crisis,
remember we must always be
they're
cautious
private
about
over here. He's
derivatives.
like, I'm definitely getting
in
gas.
general relativity, we've already learned
by the
that
time,
we can come a crop
yeah,
up
by the
if we
time I'm
take
done
ordinary
vibrating over here,
derivatives.
my tank will
we
be on.
need to go for the covariant derivative. So let's take the covariant derivative of this tangent vector, dx mu by d tau, and from equation 7, which should be on the screen, you can see that that will essentially be the ordinary derivative plus a gamma term, which I won't fill out, but there is a gamma term. Remember, that's the correcting term. And what we can say is for the geodesic, this term must equal 0. So you've got
Good.
this term plus this term equals 0. Let's look at this term here. This is essentially a double differential with respect to time. It is, if you like, d2x.
You were welcome to come into my village, Xerxes.
d
I
tau
promise you,
squared.
if you start putting your brothers inside,
What does
here,
that
it's gonna
look
be
like?
war. I had a plan.
Isn't that
You fuck up that
acceleration?
plan, and it ain't the fucking best
The rate
corn
of
cob
change
you got over there. It
of
ain't
the rate of
happening,
change of
cowboy.
distance with time.
You know the game.
d2x by dt squared is acceleration. And that equals, well, if that plus that equals 0, this equals minus the gamma term.
Because you're going to get over here. You're going to tell me
Well,
some
what does
shit
that
about
look
your
like?
Pope. I'm going to tell you something.
Let's remember
you live at my
that
house.
general relativity and Newton's law of gravitation need to be the same when you're just talking about ordinary masses.
Yeah, I saw that,
ordinary
brother.
speeds,
I seen him
low
out there
speeds.
shitting in the field.
You're not talking
God,
about
I'm
black
putting
holes,
up with it.
because Newton's law of gravitation very nicely describes what appears to be gravity. And so, in the simple case, general
Around all day
relativity
chasing
and
those
Newton's law
freaking nymphos
must
over there on the
conform to the
plantation
same
farm.
thing.
You were there. You
Newton's
know.
law
Look,
says that
why would I?
force
Why am
is
I
mass
triggered?
times acceleration. Or if you like, that acceleration is a force term
Alright.
divided by mass. And here we've got an acceleration is equal to minus a gamma term. So what we can say is that that gamma term
Apparently
is the
fine. Me
equivalent
over here
of
having nothing to do with your done.
force in Newton's laws. And there'll be a mass term in it as well, but mass is constant, so let's forget about that. This gamma term, this Christoffel symbol, has a kind of broad equivalence to force. Now, to save time, I've just rewritten equation 9 that we
You
derived
thought
for the
that's what it was,
Christoffel
Pharaoh.
symbol.
You thought that it
And
was going to
remember
go
we
any
said
other
that
way.
it consists of metric tensor plus derivatives of
River.
the metric tensor. Now let's consider a situation where we're talking about low gravity, low speed. We're not in black holes, we're not anything like that. It's just ordinary space, slow movement. General relativity must reduce to Newtonian gravity. When that happens, G becomes 1. And the derivative terms are very, very small, with one exception, and that is the time term. And time, remember, has mu and nu equal to 0.
Like, well, I want the
So
bar
the
thing to work on the battlefield and get
00
the general's
by dx
daughter to suck my
time
dick right now.
component
It's tough. Whew.
is the
Now, that's a
only
tough math
term
problem. You said you'd have to
in
get
the
her out
derivatives
here, then
that
stop
has
shooting
any
at each other,
significance.
set the
All
beds
the
on the
rest,
sheet.
when
Why
you're
don't you
talking
do
about
math?
slow speed,
I try math.
small
Maybe I can get
masses,
you.
no black
If
holes,
you do math here,
all
you
these
got
other
just got to
terms
play with
are
time a
very,
little
very
bit.
small.
Deal with the Reaper.
The only one that has
ECG,
any
man, put it to
significance
10.
is the time term. And this term G becomes 1. And so that gamma term reduces to a half. That G becomes
really
1,
here?
so we
I
can
don't
ignore
care.
that, multiplied by all of this lot, which is simply dg
Sometimes you clock
0,
in
0
and else they
by
have stuff
dx.
done. Sometimes they don't. You gotta fill in
And
the
that,
gap.
we said, was equivalent to a force term. So the force is kind of equivalent to this term here. But in Newtonian mechanics, force is minus
in some private
the
cabinet,
derivative
not in front of you
the
because you're still the
potential.
kid. But you got to figure out how to get in that room because then you'll know
For
who
example,
it is, about what
if
it
the
is, and
potential
actually know how to
energy
fix
near
about
the
it.
Earth
And you triple agent your triple
is
body
equal
all
to
the way over there.
mgx, where x is the height above the Earth, then the force, it will usually be given as minus mgx, of course, then the force will be minus d phi by dx, which equals minus
Because it's
mg.
usually I want to run a rock. What do you mean?
The minus term simply indicates that the force is
I
acting
want to
in one
stand here for
direction.
10 hours and
X
burn
is
rock,
measured
man.
in
That's
the
really
other
all I want.
direction. So all I'm showing here is that in Newtonian mechanics, force is minus the derivative
I wanted to get
of
off
the
of here
potential.
and start pulling the saws on the crew.
Now,
I
we
had
just
plenty enough
showed
rock to do
that
it.
the
The
Christoffel
fact is
symbol,
that
capital gamma,
in the money equation, you
is
want
the equivalent of a
all
force
the
term,
money.
and in ordinary space, where we're
It's gonna
not
cost
anywhere
you.
near black holes, that it equaled the derivative of the time component of the metric tensor with respect to x.
The
And
kid
we've also
doesn't know
just
anybody
shown
yet, and you gotta have the book.
that force is
Yeah,
minus
this is your part
the
with
potential.
You know how long it
of
took me to do
derivative
this?
of
I'm
the
handing you
potential
this book.
with
Took me
respect to
5
x.
years to figure out making 90-day methodology.
So we can
and if
see
I
that
told
if
you to
gamma is a
vanish
force
manuscript,
term,
this
that
pretend you're
these
the
two
goddamn, you got
terms
invoked by the
are
devil
broadly
today, son.
equivalent.
And you write that
And
fucker
thus
out
you
in
get
3 days,
that G naught naught
2 hours,
is equal to
5 minutes.
2 phi plus a constant from the integration that you need to do, but you can forget all about the constant because as soon as we differentiate again, that constant will go.
Couldn't help it.
There is probably a minus sign in there somewhere,
Yeah, life
but
of pi.
we
You
don't
rip
need to worry
that
too
goat
much
through the
about that
cage
either.
here.
We're looking at the principle here. What we're saying is that because the Christoffel symbol equals that, and Christoffel symbol has a kind of force equivalence, and in Newtonian mechanics, force is equal to minus the differential of the potential energy, that you can therefore
have
equate
evolved
these two terms.
sanctuary is
If
what
you
I want.
equate those two terms, essentially, the metric tensor, or the time value of the metric tensor, is equal to 2 times the potential energy plus a constant. Now we said that force is minus d phi by dx, but of course
When you get away
we
with
really
it.
need to do that in 3 dimensions, and so that normally reduces to what is
I
called
made the joke.
the
Your butt has to
divergence
break
of
down
phi,
the universe for Jill
where
Sargent. But
the
Jill
divergence
Sargent.
term
But
is simply a
you-
d by dx plus a d by
Not your
dy plus a d by dz term.
This is a timeline. You're on a clock. My job is
And
to
that, of
make
course,
sure
should be
you don't get
minus
there as fast
there.
as possible. So
But
we're
we
gonna go real
also
fast,
know
real far.
from Newton's law of gravitation that the force is equal to minus g,
Work it. Work
the
it.
gravitational constant, times the mass of one object, times the mass of the other object, divided by the square of the distance between them. So let's
Send me
consider
money at the
an
coffee, guys.
object
Like, 'cause
of
it's-
mass
I'm not
m,
gonna tell you to pay me the same thing you pay the
and
programmer
let's
in that
consider
coffee
a
room, but
distance
it's like
r
does inside
from
of there for
mass
$15 an hour while I'm graphing this. Taking
and
my
we ask
time,
ourselves
doing
the
my
question,
numbers.
what is the force
You come in-
acting
you come in
on a
mild.
unit mass
You better have fucking marshmallow
placed
for me.
a distance r from m? Well, if the unit mass, that means the unit mass is 1, the force will be minus gm over r
Remember
squared,
how it
because
felt
m
when you
is
fell
1.
and tripped your knee and they loved you?
What is
so?
therefore the force capability across the whole of that surface of that sphere? Well, that's going to be the integral of f dA, where dA is the area of the surface of the sphere. And that's going to be the integral
Be one of your best players.
of the force, which is minus gm over r squared, times
Sweet to me,
dA.
yeah.
Well, if you integrate out, that of course is simply going to be equal to minus gm over r squared times
You didn't hear?
the entire area of the surface of that sphere of radius r, which is 4 pi
Fear,
r squared.
anxiety, stress.
R squareds
Sensor.
cancel, and so you find that that reduces
Gradient
to
lap, yeah.
minus
Pitch on the roof.
gm times
Being up there on a
4
hot summer day.
pi. Now there is a theorem called the divergence theorem, which I won't derive, but you can look it up. I'll write it out first. It says that the integral of f dA over an area is equal to the integral over the volume of del f dv. And what that means in layman's terms is that the outward flux through the area of a sphere is equal to the volume integral of the divergence of the force. That's just a divergence theorem that can be derived, and you can look it up.
Move the tomato plant.
I also just want to remind you that density is mass divided by volume, and that therefore you can say that the mass of an object will be the integral of the density with respect to volume. So now I'm going to take f dot dA, which we calculated to be this term, and set it equal to this term. So you've now got that f dot dA is 4 pi g times m, or more accurately minus 4 pi g
I have a video.
times m, but for m I'm going to use the integral of rho
I've used
dv.
an AR-15 before, and I have the same number.
Density times volume. That's f dot
Bell's
dA.
quality. I got you, Belly.
Or more accurately, this is the integral of f dot dA.
Both.
And that's going to be the integral of the volume of df dv, or del f dv, the divergence of f. Well, although it's not really proper to do it, you can cancel out the dv's.
Yep, I'm dead.
Essentially what you're left with is that del f, the divergence of f, is equal to 4 pi g rho.
Travel down the black hole, boss.
Actually minus
Therefore,
4 pi g. Unfortunately, I had a camera failure for the next section, so I'm just repeating the flow of the argument. We've shown that the force is minus the derivative of the potential in Newtonian mechanics.
Which one were you talking? Oh, no.
We've also just shown
carry the one.
that the derivative of the force is equal to minus 4 pi g rho. Consequently, if the force is minus the derivative of phi, the derivative of force is the derivative
didn't hit me with the right answer in the
minus
paperwork, but the form I already have done one.
And that equals minus 4 pi g rho. In other words, minus the derivative squared of phi, the potential, equals 4 pi g
You want to
rho.
smoke that boss
The
in my
minuses
mill,
on
man.
both
You gotta have
sides
that marshmallow.
cancel.
I'm not gonna let you pass in terms of doing it
Earlier we
unless you
showed
tell me in the Sharp's
that
case he
the
earned it.
time component of the metric tensor G00 equals twice the potential plus a constant, which means that the potential is half the metric tensor. I've dropped the constant, but you'll see there's no problem about doing so, because as soon as you do a derivative of phi, derivative squared of
on
phi,
the ones and zeros, and 1, 2 I had
this
Bernoulli's
term
that I was
here,
doing, right? Yeah,
replacing phi by half G00, the constants will all go, of course. So now you've got that the derivative squared of phi is 4 pi g rho, so the derivative squared of half the time component of the metric tensor equals 4 pi g rho.
You let me deal with
and if
that.
you multiply both sides of the equation by 2,
Watch.
you get
I know you.
that the derivative squared of the metric tensor equals 8 pi g rho. The problem with that is it's not a tensor equation, and for general relativity we need tensor equations. So what we're looking for
stuff, buddy.
is something that looks similar to it, but where on the left hand side of the equation you've got a tensor, and on the right hand side of the equation you've got a tensor. So we want something that has the form of g mu nu,
I cracked down
which is
into an energy
Einstein's
generator to pull out some
tensor,
Z-coin.
is equal to 8 pi g, but instead of having the mass density term rho,
Space.
we want
who can do the concrete pour
tensor
here for footage?
energy, something that contains all the mass, energy, stress, pressure terms that you can have. So we've essentially got to find something for this and something for that. Let's look at the T mu nu side of it first.
Just lay down, Einstein.
If you go back to my video on special relativity E equals mc squared, part 5, and go to the point in the video which is 2 minutes and 10 seconds
what is it
in,
you got there?
you'll find that we derive what is called a momentum 4 vector. The 4 vectors, of course, 1 dimension of time, 3 dimensions of space. And you'll find that we define that momentum 4 vector as being mass multiplied by
Archimedes,
x0 over tau, x1 over tau, x2 over tau,
that brother is like,
and x3 over tau.
None of this is coming back to Rome.
And this is simply, obviously, that's the time component, the x component, the y component, and the z component in the 4 dimensions of space-time, divided by tau, proper time, the time that everybody agrees. And what we showed was that if you reduce this term, you get essentially an mc squared, which is energy equals mc squared. And these terms all effectively become the momentum in the different coordinates.
Eschatology.
So it's mv in the x direction, mv in the y direction, and mv in the z direction. So this 4 momentum reduces out to basic rest mass energy plus momenta in the 3 coordinates of space. Well, that's fine, but that is just, of course, essentially a vector.
Right now, somebody give me a
we need a tensor. We need not p, but t mu nu. And that means we need a 4x4 matrix. And to save time, I've drawn one. And there it is. You will see that t has all the values of mu and nu from 0 to 3.
Well, it's not that. Yeah, I know it's hydrogen. It can be anything else. I don't care, and you don't do it any other fucking way.
That is going to be the time component.
There's a whole bunch of Hurt Locker waiting for you, turning over rock, telling me some other things different. There's already a bunch of people that do that.
And that has this kind of equivalence. It's the energy part of the tensor.
Stone mill.
The 3 components along the top here
of the face of the blocks when they're coming in on the perfect square.
The tensor. The 3 components here are what are called the momentum density of the tensor.
Why?
And the 9 components which are left are essentially
these values in this form, it doesn't really make sense because they would be different if I wasn't running the tread line or something.
In other words, we are embodying every part of energy that we can think of, whether it be pure energy, rest mass energy, momentum, stress, all of it somehow finds a place.
It's like, as long as it's fixed under that model, it should be my codes or anybody else's code. Now it'll be a time fraud case about some other stuff later on.
It is, if you like, a measure of energy per unit volume. Now, energy has the same units as work, so we can think of this as work per unit volume. Work is force times distance. Distance is a length. Volume is a length cubed. So that's equivalent to force divided by length squared,
regular union stuff about the worker, brother at LEGO, you know what I mean?
Pressure. So that's how energy per unit volume can also embrace pressure or stress. So that's given us, we can't derive it, but I'm trying to illustrate how we get here. That's given us a stress energy momentum tensor.
And I don't want you to make another move outside. Remember when he did that backwards? And right there? Brick. I need that in a straight line at n1/2, n1/2 square wave, rocking this thing, NP forbidden, all this, the path, so it is laid out.
Of the Einstein field equation. So now we've got, on the right-hand side, we've got the 8 pi g that we derived. But we're going to replace the density term that we came up with this new
I'll do that for you.
Stress energy momentum tensor.
You should help. Don't be a punk.
And we're going to have something on the left-hand side. Now, what could it be?
Energy in it. Could have been in.
This is, as it were, the mass term. On this side, we need something that is the space-time curvature term.
I want to
so
feel
Einstein thought that the obvious candidate for it would be the Ricci curvature tensor, R mu nu. But there's a problem. The problem is that we have a thing called energy conservation. Energy can be neither created nor destroyed. So if you take the derivative
about why I need to be in a women's feminist class, I'll be like, yeah,
there is no change in energy.
You should do that.
The problem is, if you take the derivative of the Ricci tensor, it does not equal 0. So that equation can't be true, because the derivative of one side would be 0, the
Like I was
derivative
supposed to
of the other
burst in
side
flames
not.
on there or something.
Bear in mind that we must always, when we're talking about general relativity and field equations, never do ordinary derivatives. You will come unstuck. We must always use the covariant derivative. So if we've got that the covariant derivative of the energy side
it's just
is 0,
it's a safety manual on the machine. Just for some reason you look up off of it and it's like, oh, warning. Oh,
0.
yeah, I remember now.
Now, what Einstein actually found was that the covariant derivative of the Ricci tensor was not 0,
every once in a while.
but it actually was 1/2 times the covariant derivative of the metric tensor times the curvature scalar, which we spoke about earlier. If you've got an equation like that, you can bring everything to one side, and essentially you get that the covariant derivative of the Ricci tensor minus
famine, well, conquest
half
here.
times
Just being
the
hiding in
metric
anything's
tensor
form, but
times the
also
curvature
war,
scalar
the reaper
equals
over
0.
there.
And now we've got the covariant derivative of a term
X, Y, and Z.
which equals 0.
Well, for me, it's a quadrant on a chessboard.
We've got the
I just break it
covariant
down into
derivative
eights.
of TMV
Right?
equals 0.
Yeah, eights on
And the
what it
covariant
is for the
derivative of
chessboard.
this term equals 0.
And then you have a
Therefore,
gambit
that
on
term and
again
that
with the
term must
multi-matrix
be equivalent.
when this is
And so we've
something
now
playing
got the
something different
left-hand
in a different
side
equation.
of the equation, r mu nu minus a half
Are they? Yeah.
g
I have a
mu
standard
nu
model out
times
there that makes my
r
M1, M2 when I'm thinking about
equals the right-hand
the
side of
integration
the
of
equation.
an
Well, it's not just
MIT integral
T
to
mu nu, of course,
Schrodinger
it's
field
8
theory
pi
means
g
I've hit a field
T
theory
mu
on the
nu.
floor, and I know what an integral is of two sets. You put them together, and that's where the shift and heats a lot are.
And
they
we're
have common
almost there.
names.
It
They have
turns out for
truck
dimensional purposes you
pallet
need to have
operation,
a c to the
dumpster
fourth
observations.
term
They have a new
here, but that's
value.
essentially just a
And
constant
that's going to be as much
for
causal
dimensional
to loading
purposes.
up the saws.
But
Beat
Einstein
that didn't
realized
have a
he'd
sawyer that
forgotten
could
something.
run
You
a
remember
machine,
that earlier we showed
and therefore couldn't
that
dump
the
and messed up the
covariant
whole timeline.
derivative
But they were
of
cranking like
the
crazy on
metric
that saw,
tensor equals 0,
and they were good.
because it did it in one frame and therefore it must do it in all frames. And therefore we could have included the
Going in, boys.
we could have included the metric tensor in this equation here, not just as a multiplier of r, but in its own right. And of course, we could have included it with any constant in front of it.
Here, man.
So Einstein therefore decided that you needed to include this term in this equation again.
They will run around
So
like
now
it's
you
a toy.
need r mu nu minus a half g mu nu r, which is this, just this term here. And now you need to include the fact that you could have had a metric tensor term in here. So we'll add it,
Now it's just imaginary one you can't touch.
and we will have a constant which we'll call capital lambda multiplied by the metric tensor, and that equals 8 pi g t mu nu
Getting
divided by
good here.
c to the
I'm
fourth.
getting good, brother.
This part, you'll remember, was the Einstein tensor g mu nu. What is this capital lambda term? Well, it's called the cosmological constant.
What is the cat in
And
that? Is
curiously,
he alive or
it is
dead in the
the
mission
constant
where he put him in the
which
box with that
Einstein
radioactive
first thought of
isotope for the
way
simulator
back
training in the
when he
D-suit?
was trying to identify how you could describe space in mathematical terms. Now, he was being told at the time that space was fixed and unchanging, that nothing moved in space if you looked at it over a huge cosmological time and space frame. Obviously, the Earth goes around the sun. But generally speaking, everything stays as it is. That's what people thought.
Any day,
And Einstein said, well, that can't be right,
Any
because
day.
gravity would tend to make all the galaxies